Okay, let's see how it goes. Okay, so so a native language means somebody, if you're speaking in somebody's native language, you don't need a translator in between. That means that you are speaking directly to the recipient in the language that it natively understands, that it's wired for. So the computer basically understands one language. And that language is, and this is, similar to, that's a light switch. That means that it's either on or off. And that switch essentially is, electricity running through those wires. That's ultimately a microchip is basically a collection of circuits and gates that turn on and off switches. Let's put so let's put it as, which whenever somebody tells you that a computer understands zeros and ones, that is basically saying this switch is on, this switch is off. And this notation, because there's only two numbers, it's known as binary. That is essentially like, that is binary notation, where we are arranging a bunch of zeros and ones in a specific way that it might mean something. So if we could convert that, like convert the number 0010 like that, this is a number 5. And again, well, this thing, I'm not saying it again because I'm saying it for the first time, but from a perspective of why would something that looks like 101 would be 5? And it is because any number, it is whatever the base is, to the 0, base to the first, base to the second, base to the third, base to the fourth. This is assuming that we have only 4 characters. So in human speak, it would be 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3. And in each one of these guys is basically that number, whatever number that we put in, from 0 to 9. So essentially from 0 to that base. And if I am actually like confusing you guys, please stop me. But if not, I'll ask for numbers in a second. So for example, in the 0 to that base, in the base 10, which is what humans do, we know that our digits are 0 through 9. Once we complete that, then we put a 1 on the other side, and then we start counting again. And then once we complete this guy, we put a 0, and then we put a 1 in here. So it's kind of like, as you are progressing through some of these numbers, why is it not resetting? There you go. So for example, 9, and then like, you can go like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the next one is, once you get to that 0 again, you add 1 digit. Essentially making it number times base to the position. That's essentially the formula of each digit. Again, this number 10, it means that it is 10 to the 0. That means, and it just as a calculator. I'm going very, very technical, no, very scientific here, but I want to explain that. So if I go 10 elevated to the 0, that's a 1. So then it becomes, the number 19. Let's just grab the number 19, becomes 9 times 10 to the 0, which essentially becomes 1. It becomes 9 times 1 equals 9. That's what that number means. The second digit becomes 1. Let me just scratch this. 1 times 10 to the 1, because it's in the first position. 10 elevated to 1. It's 10. 10 times 1, it's 10. So that's 19. That's basically how all the notation of all numbers work. Now, if you reduce what humans have for 10 into 2, then your only digits are 0 and 1. And where 2 elevated to the 0 is going to be 1. So this 101, it's 1. Then the other one is we don't really care about that 0 because it's going to be multiplied by 0. So it's 1 plus 0 plus, then we're going to go for this one, which is 2 elevated by 0, 1, 2, 4 times 1, it's 4. So 4 plus 0 plus 1 equals 5. 101 in binary equals 5. Is a 5 in our digit. So we're translating from computer speak to human speak. Now, I don't want you to memorize any of this. I just want you to more or less understand it, because this is where we go back into the native stuff. Let me just ask for numbers, and let me add a separator here, just so that I know. If more or less you understand what is a notation, and if this is somewhat clear for you. I know this is like the first numbers that we're asking, and it's not very concrete. I know that also it's not going to be something where we are going to quiz you about or anything. I just want you to more or less understand it so that you understand how things work internally on the computer. So let's do some numbers, guys and girls. 10, 10, 10, 9, 9. Okay, Sareth, what part can I make you understand better?
No, I know it's nothing we can need go over too much, so I just put that just to like it's how to like really pay attention to it more.
Okay, yeah, and that there's there is books and books and books on this, but now that we understand how do we translate from a bunch of zeros and ones into a graphics card or a letter or anything to represent the world, it's just basically how we are encoding all that information. So that's basically what I want you guys to understand, that it translates it from switches that are aligned into information for us. Now, all these switches, the computer natively understands numbers, data, and a specific set of instructions. That's basically what a computer processor is understanding. And all of it is represented via just binary information like this. That's the language. Now, the set of instructions is a set of things that the processor knows how to do as basic as possible. So it could be like, bring this from memory. Let's add this number with this number. Let's store it here. Let's send it to disk. Those are the very specific instructions that it understands. Like very, 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 very extremely basic stuff. And all those instructions is basically just telling the processor, do this with this data. That's it. As simple as that. Now, those instructions, that collection of numbers, data, and instructions was essentially the first programming language. The first programming language is called assembly. And that assembly language actually, if you guys ever saw pictures like this in old school, actually you guys have seen quizzes and voting stuff like this, but the first computers, actually this was the first programming language where the programmers would encode instructions into a card that the computer knew how to either pass light or block light in order to translate it into those switches being on or off. That was like the very, very, like this is in the 50s. I mean, now this thing, the phone, is dramatically much more powerful than those things would ever be. But those were powerful enough for the time. But that was basically the first programming language. Now, programmers throughout the history of programming languages, they were like, okay, you know, they always try to automate things and make things better and make them last, or try to make the task of a programmer to be as fast as possible. So then they started adding, okay, well, what if we started adding somehow something that resembles some English? And that's where certain basic programming languages started, like C, where some concepts were introduced, like the if, conditional, the loops, I don't know, a bunch of different basic programming structures were introduced just to give us some better interaction with a computer. This was impractical. The punch cards were impractical, so we needed a way to like try to speak some language to the computer. So I'm not going to go through like the full history of all the programming languages, but this is to explain that there are low-level languages and high-level languages. So we have different ways of of using those languages for different things. If I am writing the drivers if I was hired as an engineer at NVIDIA and I wanted to write the drivers for a graphics card so that I could write CUDA instructions and mine Bitcoin or something like that, most likely I would want to squeeze every single CPU or GPU cycle. And if I am at the lowest level and I want to extract those cycles in the most highly optimized way, I would probably do it in assembly. And actually, there's a new technology called WebAssembly, which is not exactly like as assembly, but it's trying to like go as low level as possible to make the computer use the browser as native as it can be. And you know, as we have been adding languages throughout our life, you can start seeing that languages like Python, that some of you guys have experience with, that is much more readable. And the more readable or the more human-like that it is, it tends to lose internal power because there's more processing that the computer needs to do to translate from the higher level to the lower level. Now, I like to say that this higher level is kind of like the ultimate programming language. But like, for example, hey Siri, set a timer for 8 p.m.
I turned on your timer alarm at 8 p.m.
I said, like, set a timer, which is absolutely the wrong thing to say. But this thing understood that I wanted an alarm and set an alarm for 8 p.m., which is when the break is going to happen. But you see, the computer had to jump through different hoops to try to understand what I wanted to say and deliver that. So Siri technically is a high-level programming language. Siri, Alexa, the Google Assistant, all those things are high-level programming languages, if you want to see them that way. They understand whatever thing that you want to say with whatever grammatical flaws or even disabilities or things like that, and then retranslate it to a set of instructions and ultimately make it to the computer. Now, all these languages, every single language, essentially at some point shares, can the term low level can be used interchangeably with native? Yes and no. Native is essentially that it's assembly. You are speaking the computer's language directly. But C, as a programming language, is a lower level language than, say, Python, but it's not native. Does that more or less explains it, George?
Yep.
Okay. Yeah. So it's tricky. So the only native is assembly, because let me put it. I was using Italian on earlier, but French, for example, even though that it's a Romance language, there are parts of English that are closer to French than what they are to Italian. But if I want to speak native to you, I could probably say a few words in French, and you might understand it as well. It's not native, but it's close enough. It's a lower level language, closer to native. Let's get me some numbers for this part. Sweet. I'm doing my job. Okay.
Wait, I have a question.
Yeah, tell me.
So, assembly is not binary though. So, how is that native? Does it translate into binary? But it's not. It's also a language itself.
Yeah, it's a direct translation basically. The only layer of between assembly and this is like if I show you like some examples of assembly language. Mm-hmm. Actually, the better analogy is that assembly is what the processor understands. How does the processor handle that? It's electricity. Same thing as saying English, but your brain is not really like working in English. In reality, your brain is working on electrical currents between neurons, but still your native language is the set of instructions or the language that you just absorb directly.
Okay.
In assembly, like for example, just to show a little bit of an example of code, each processor, just I'm going to put these guys here side by side. Each processor has a set of registers where it puts instructions. So a lot of times it would be like move from this instruction to this instruction, and then you move from this instruction to this instruction. So it's essentially like saying we are changing from this register to this register, whatever it was. And then sometimes it might mean like bring from memory whatever information. So it would be like, okay, in order for us natively, if we were doing 3 times 2, for us, we just applied that operation. But in assembly, it would be bring number 1 from memory, put it in register 1. So, okay, we put it in register 1. Then bring number 2, put it in register 2. Okay, now that we've moved both of those, then let's multiply both, whatever is register 1 and register 2, and then store the result on register 3. And then we want to display it. Well, we're going to send it to the monitor, to this particular address, and display it that way. So it's much more slower to put it that way. I mean, slower to explain it, but it's super fast because it's just essentially the very native instructions that the computer, that the actual CPU understands. Did that clarify your question?
Yeah, it did. So like the punch cards are programmers actually just punching in the 1s and 0s.
Yeah.
Okay. Nice.
Yeah. That was whenever you speak to somebody like I think a friend of mine, his dad was a computer science major, like in the 70s or in the 60s, and back then for school you had to like bring your punch cards, and then you had like there was no laptop, so they only had one computer in the lab, and if you made one mistake, like imagine just in your set of instructions, and then on the last instruction you made a mistake, you had to start over again and repunch everything, which is painful, as opposed to just deleting one character and recompiling. So programming was a lot more difficult. So that's why we went into trying to like make them as high level or as low level as possible to try to have different ways of interacting with a computer. Now that we understand this high level versus low level language, and a lot of these might be parallel, you know, like you know, I don't know, Python and Ruby, I would put them in the same horizontal and things like that. But just the same way that if I put Sareth with George speaking in their native languages, if I put Sareth speaking Cambodian, unless I'm terribly wrong, George might not understand him, and vice versa. So if you have two languages, language 1 and language 2, whatever it is, even if it's native, you need a way to send from one language so that the other language is understood. And usually whenever you have that communication where it's in two different languages, we often rely on a third party that would be a translator, right? We would create, let me just go in here and actually, let me make it a little clearer. Translator. So if we wanted to go from level 1 and level 2 to level 1 to level 2, we would need such translator. Same thing if we are in, you know, in Python, we have to translate directly. From Java, we have to translate. So a lot of the times, certain languages have what it's called a quality of, or it's not even called, but I'm trying to explain it in a simpler way. There are translators, like, I don't know if you've ever seen like in the United Nations, how the heads of state and things like that have like a headset and they're speaking their native language. And then you suddenly see the, I don't know, like you see the prime minister of Germany, and right next to the prime minister of Germany, there might be like the president of India. And you see, I don't know, Angela Merkel speaking, and you see then Modi just nodding. It's because there was a live translator through the headphones translating live so that they could work together and understand each other. So with those live translators, the translation is pretty good, but not perfect. What do I mean? Like, it's not perfect. If you were writing a book, and then, I don't know, you wrote, let's say that that Jose wrote a book in Spanish, and then he wants to you know, he became good friends with Nadia, and Nadia is like, you know what, I would love to take your book and into some of my family that I have in Nepal. Let's make this happen. If we put it through a live translator, one of those live translators might actually make it work okay and be semi-understandable, but since they have to translate really fast, they might not make the right word selection and might end up losing certain concepts of the beautiful poetry. If we had a live translator from Spanish to Nepalese, is it Nepalese the language, Nadia?
Yeah, you can say Nepalese.
Okay.
Nepalese or Nepali.
Okay, Nepali. So if we're translating to that, and if we're doing it in a live translation, might work, might not be fully ideal. And you know, at the end of the book reading, maybe Jose might not be very satisfied that some word got translated weirdly. And that's, you know, the nature of just translating quickly. But if you're translating a book, usually you give it to a translator and somebody that actually can reproduce in a faithful way to the author what were the ideas or the concepts that were translated. And in those cases, there's a lot more thought process going into what are the words that I'm going to choose to like properly translate this, or even you would call it as optimization. So in the computer, there's similar cases for that. And when we are translating something live, we're optimizing, but not fully optimizing. We're not making the best decision possible because it's made on the fly. And those languages are known as interpreted languages. They need to be as fast as possible, the translation from that language, the high-level language, let's put it as high-level language, all the way to the native language. It has to be fast. Let's draw a lightning bolt in here. But if we are going to be doing like another language like precompiled, there's from any level language, let's even say a high level language, all the way to native, it's a little bit slower. Let's put a timer. It's a little bit slower, but more thoughtful. And I'm drawing a brain here. Doesn't look like a brain, but that's basically what happens. So now what are examples of languages that are interpreted that need to be fast, that there's not that process of optimization and translation? Well, example of those languages of this one interpreted would be JavaScript. JavaScript is read from the browser and it's higher level language, and it gets translated into whatever the local thing is. Python, for example, Python is interpreted, and there's some, Ruby. There's a bunch of languages that are done that way. Precompiled, that means that you had more the chance of optimizing things. So some languages like Java is precompiled. C and C++ are precompiled, and that's why they can return that. That's when they can be very, very, very optimized for some operations. Just as an example about Java, Java is extremely fast because not only because the runtime is extremely fast, but also because the compiler does an excellent job at removing things that are unnecessary and even predicting how the code should be optimized for the fastest execution. I would like to get our interpreted and precompiled languages all high level. They are higher level than assembly. So C is, not as high level as Python, for example, but it's a higher level than assembly. Did that answer your question, Josh? Okay. All right, so I'd like to get some numbers then on these interpreted and precompiled. Yeah, you can resume your Zoom. Actually, I'm gonna give you guys 20 minutes of the break. I'll see you back here at 8:25. So that way you can plug in your computer and hopefully find even a new spot for so you don't miss out on the slides. But if you're seeing it on your phone, that's probably fine. You might not read all the text because it's going to be tiny, but let's see you guys here, guys and girls, at 8:25. Okay? Okie doke. Is everybody back?
Yes.
Okay. Cool. Guys, I prefer the cameras on because that way I can see reactions. Just it's a good also feedback indication. You guys can nod, and I'm not just waiting until somebody actually types something. There you go. Thank you, guys and girls. Okay. So we left it at the interpreted versus precompiler versus native. And the only other concept that I want to cover here that it's, I think, relevant about languages is what it's statically typed versus dynamically typed. What does that mean? Well, when we are defining something in a programming language, that something is going to be, say, a number as a variable, you know, let's even describe it in a certain way. So we have a variable that we are describing it as a star. Throughout its life in the program, it will, once declared, it will always remain a star. You know, like, actually, let me put it this way. Like, I'm putting it inside of a house. And this is, once we say, okay, what I'm storing is a star, it's always going to be a star. Where it is a blue star or a red star, those things can change, but nonetheless, it's going to be a star. In the case of, and this is what it's known as statically typed, meaning once declared, that's it. There's not changing the type of object or the type of item, right? So we're storing it in that memory block that it's this guy, the circle here, and that's it. Now, in the case of dynamically type, well, first of all, what's the difference between static and dynamic? Who can tell me?
Static is constant, dynamic is changing.
Correct. That is absolutely correct. So if it's dynamically typed, you could be describing that inside of this memory space, I'm going to start with a star. Oh, I didn't do a good job at that. And then throughout the life of the program, the next time I want to change something, I may actually declare it to be a circle. And then a little bit further down in the program, I may actually change it for a square. And then on a further part down the program, I may decide to change it for a pentagon. So that means that the programming language allows to change the type of the object, regardless of what we are storing. Meaning, let's try to translate it to a language. In languages like Java, you have to declare what is the data type that you're going to store, then the name, and then, you know, whatever initial value. In the case of languages that are, this is statically typed, I cannot go ahead and later say, okay, no, it's going to be string A now, and we're going to change it to a default string. I cannot change that. Once I declare that it's an integer or a number, in a statically typed language, it stays that way. In the case of a dynamically typed language, I can go say, for example, in JavaScript, I can go say var A equals 0, and then I can say A equals hello in the next one. This is a string or a set of characters. This is a number. In this case, I cannot change that. In this case, I can, because I can change the shape throughout the execution of the program. Let's get some numbers for this concept. Statically typed versus dynamically typed. Perfect. So Java is a statically typed language. And for that reason, you know, it has advantages and disadvantages. It has the disadvantage to the programmer that once you create something, you cannot reuse the same name as a variable. But it has the advantage that once you create something, you cannot reuse the same name variable. It all depends on what is the side that you're looking at the situation with. And if you noticed, I repeat the exact same phrase as both a good thing and a bad thing. Why would it be a good thing? A good thing because I cannot all of a sudden decide that I'm going to put a different value where I was expecting something else. Like, for example, I cannot say that it's a number when I was expecting a text. So, for example, name, the keyword, or like if we're storing a name, and we're saying string name, I am forcing the variable name to have the contents of a string or a text by saying, I don't know, let's Brandon. That's what we're storing. Now, if I wanted to store in name equals 10, the compiler would be like, what are you doing? This is a string. This is not a string. What are you doing? The computer would forcefully complain about that. Now, this could be an advantage because it prevents us from doing something silly, but it's also a disadvantage because it's inconvenient to have to be not renaming things if we needed to. So it is both an advantage and a disadvantage. The authors of Java considered it an advantage because it makes it a little bit more secure. It makes it more predictable because you know what an object is going to return at all times. It's not like accidentally I was saying, oh, well, a function that I'm supposed to reply either yes or no, all of a sudden replies 4. Well, what do I do with a 4? Is it yes or is it not? So from that perspective, it brings consistency. Okay. Any questions about any of these statically or dynamically typed? I know that a bunch of you wrote 10. I'm probably staying in in some of these concepts for too long, but I just heard somebody was going to ask a question.
I have a question.
Yeah.
When you wrote, because like I just took the C# class and
Mhm.
it also is very like strongly typed, I guess. But I noticed that you used like var as a like to identify the type of the variable. But does Java have like generics? Is that
There's multiple concepts. There's generics, yes, and also Java is introducing the variable data type now, and that is because Java is trying to compete with other languages like JavaScript or Python that have become really popular. So in newer versions of Java, if we go into here, now there's the var data type that it's flexible. See, it was until Java 10 that was introduced. And it's just essentially just a way of like saying, okay, I can put whatever on it. I'm not going to define what it is. It's just variable. The compiler is doing the tricks under the hood.
Okay.
But it's very similar to that in JavaScript. Yes, tell me.
So if you're using var, if they didn't have the var keyword, is the only way to get around that is with like generics?
Generics, we'll talk about generics. No, generics it's not related. Generics is more like not having to reuse the same, like being able to reuse the same code. But there are some ways, like just by having the like if you want to use the keyword object, but that makes it open to anyone. Generics is there would be a way to do it with generics. That's probably also a reason why Java didn't introduce it, but we'll talk. I think it's class 9 or 10 when we talk about generics. I wouldn't want to introduce much of those concepts right now to avoid confusion, but we're gonna get to that point. All right. So let's then continue. So what's so great about Java? Java is, relatively speaking, an old language at this point. It was introduced in the 90s. And the reason why it was introduced is because, let's give a little bit of history on Java. The reason why Java was introduced is because you guys remember, what we were talking about, the processor. And I'm always going to use these, the processor and a memory bank for like the RAM. And we were talking about assembly. And in this assembly slash CPU interaction, whoever decided the assembly, what was assembly language looking like, was the manufacturer of the chip. So right now, the dominant chip, well, it's starting to become less so again. But basically, the dominant chip was the Intel 8080 family. Well, that was in the 80s. That's when the actual PC was introduced. Oh, I'm not even presenting them now. So the Intel 8080, if in case that I didn't have it, this is what I was talking about. Like, this is the notation that I use for like RAM. This is the CPU, and the assembly is that language. So whoever wanted their processors to be used, they defined the assembly language. So in the 80s, and now we're going back again to that tendency, but in the early 80s, late 70s, there were other different types of processor architectures. And Apple, for example, was manufacturing what was their PowerPC chip, and that was another type of chips. Then Sun Microsystems, which is now bought by Oracle, and they were the original writers of Java, and they wrote. Do you guys know what a mainframe is? Mainframes are the predecessors to the cloud. Mainframes was a thing that in the 80s and 90s, universities and things like that would buy, and it was just essentially a giant full rack that was considered a single computer. And that was, back then, your supercomputer. And, when you could hear like, I don't know, in the early 2000s, like, oh, now the University of blah has the fastest computer, usually was that they had a mainframe. And they had like funky designs, and IBM was a manufacturer of mainframes. Sun Microsystem was another manufacturer of mainframes. Hewlett-Packard was another manufacturer of mainframes. So all these guys had different processors, and therefore different types of assembly languages. So when the PC is introduced, and compilers would translate to the specific assembly language from the 8080 and the specific architecture, it was not easy to go and translate, say, Excel. Let's put all the cells from Excel, from a PC into a Mac, because they were using a different processor. And that's what actually made Microsoft the monopoly that it was in the late 90s, early 2000s, because Microsoft had all the developers at the time, and it had Visual Studio and all those things that made it really compelling. It had like a really big suite of development tools, and it dominated the market because you cannot translate your code base into other stuff. So Sun Microsystems found themselves as, okay, our computers are expensive. And just to show you a little bit of how those computers looked, even from their workstations, Sun, the computers were like this. So you either had, these funky purple, actually, who's in the Sun Microsystems campus? Now it's a big tech company. Let's find out. Sun Microsystems Silicon Valley campus. Yeah, it's Menlo Park campus is now occupied by Facebook. So where now Facebook is, that was Sun Microsystems before Oracle bought them. And there was this big, and I'm just taking you through like a history of computers and stuff like that, but this was their mainframe. And if you wanted to buy their mainframe, you needed to buy their workstation so that you could program for those workstations. And yeah, they were powerful and everything, but they found themselves in a situation where they were not going to sell any servers because there was no software for them. So one of the engineers, actually, some of the engineers had the brilliant idea, like, what if we write a programming language that allows you to write things once and run them everywhere? Meaning, doesn't matter if I write them on a cheap PC, we can run them on our Sun Microsystems system. Doesn't matter if we put it on a PC, if it's on a PC or on that. With the birth of the internet, that gave Java the capacity of being, quote, quote, the official native language of the internet. So Sun Microsystems decided to spend a lot of money on that project and invest heavily in Java with the idea of write once, run everywhere. Meaning my code that I could write here, it would run on all these platforms. How they achieve that? Well, it's very simple. If we remember the translation thing that we had before, we would have a high-level language that would be precompiled into the native language. So what if Java had an intermediate step where we precompile into an intermediate step? And this is, and then in here we would have an intermediate step where that would be read and translated between the native computer and this assembly. They were writing an intermediate assembly, which in some cases just is a one-to-one translation and it becomes really fast. But they had like that intermediate step. So then Java would provide a runtime that was known as a Java runtime environment, or the virtual machine, that, as they called it, they were the first ones at creating virtualization that would translate it into a machine. So then whatever binaries that came out of these precompiled, you can actually ship it to another computer. And as long as there was compatibility between this layer of Java runtime environments, you could grab that binary and run it everywhere. Doesn't matter if the underlying native was, you know, different flavors. You could run it because the virtual machine would do that translation. Does that make sense? If so, let's get some numbers about this concept of the runtime environment, pre-compiling and all that.
I have a question.
Yeah.
So the Java runtime environment, so that just knows how to convert the Java into the different types of assembly. That's it.
Yes.
Is it?
Yes.
Yeah, that's basically what it is. It's a translator that it's just very optimized. Obviously, the ones that started getting nervous because Java started picking up a lot of market share like this. Java became the dominant programming language for 20 years. And the people that immediately became concerned about, obviously, was the people that that dominated the market. So Microsoft became really concerned about Java getting so popular. They were like, okay, we need to introduce competition on this. What was the competition for this? Was basically a clone of Java known as .NET. And as some of you that have already taken C#, you're going to realize that C# and Java are incredibly similar. And the only reason is because Microsoft was really worried about Java. Now, for many years, Microsoft didn't provide the runtimes for different computers for the code that they were running, because they were like pretty much closed source at some point. That didn't gain them enough market, throughout all these career path of languages, Java became dominant for that perspective. Years later, just to add some color for Nadia here, years later, the people that optimized Java were hired by Google to create the V8 engine. And the V8 engine is nothing else other than a very powerful and fast and optimized runtime for JavaScript. Technologies like Node.js, they're utilizing that V8 engine to run JavaScript in a really fast way. Now, the importance of all these runtime things is that Java is extremely fast. Same thing with JavaScript. Right now, JavaScript and Java are like super fast, both of them. So super fast. I mean, we even have text editors like Visual Studio Code, that this editor, basically Visual Studio Code, is written in JavaScript. It's really, really, really powerful. Like it's super powerful, and same thing with Java. There are benchmarks that Java is as fast as C++ in some situations. Just because something is written in Java doesn't mean that it's not powerful. It's super powerful. So then what is so great about Java? Well, it's portable. We can write it once and run everywhere. Now you guys understand what that means. It's secure, or it is more secure than C++ and things like that, because it introduced concepts like memory isolation and memory management. In C++ and C, which were the languages back then, which the syntax of Java is based on. Like the syntax of C++ and Java is not very different. But the big difference is that in C++, if I want to reserve memory for an object, I have to reserve that. I have to manage that memory. And when I don't need that memory, I have to delete that memory and free it up. In Java, you don't worry about that kind of stuff. So it was like impressive that, oh, now there's this concept that I don't have to manage what I create or release resources or not. And another thing that was important, and this is something for you guys to know about cybersecurity. Back in the day, you had your computer memory completely. Let me actually put the memory like if it was big. This is all the memory on your computer. And if you had your Java or a C++ program running in this cell, a virus or something in a different cell, that virus could go and start hijacking the memory of a good program and corrupting it. So one of the things that Java forced, and now it's used, that concept along with virtualization pretty much everywhere, is that there was memory isolation. So if somebody wanted to jump in from a bad memory cell to a good memory cell, it was prevented. It was isolated, the memory. You could not go and change it. So that was another added benefit on security. It's object-oriented. It became immediately, because it was written based on object-oriented stuff, it became immediately current icon of object-oriented programming. It's robust because the developers of Java say that it's robust because of the strongly typed and statically typed, and also it has good exception management. It was really the first language to introduce exception management in a better way, in the best way possible. Then it was built in for multi-threaded and distributed environments, which, funny thing, when the guys from Google started their thesis, which essentially became Google, they chose Java because it was multi-threaded and built for distributed environments. And essentially Google is what it is because of this, because of these multi-threaded built-in capabilities. Before, you had to jump through a lot to actually make something multi-threaded, and Java made it simpler. Now it's complicated compared to other technologies that we have built, that it's a lot simpler, but it made it a lot simpler. And it's super fast. And well, this when I wrote this slide was that it was a second most popular language on GitHub. Now it's the third. I just showed you guys earlier that. Okay. Any questions about this Java greatness? If not, let's go get some numbers. How often is the programming system updated? Java now it used to take a lot longer to release stuff. Technically speaking, Java is still on the first version. Like when it was released, Java, sort of. I'll explain that in a second, Josh. But the Java is technically still on the first iteration and the first version of the programming language, because right now Java is on version 1.15. Now they're calling it Java 15 because they haven't dropped now they want to drop that one, but the language has evolved at the very least 15 major iterations since its inception in 1994, 1995. But now it's updated more frequently. There's reasons for that, but before it was like not updated as fast as it should have, and other languages gained terrain. Now that's why Java is introducing. Okay, Java 10. Actually, let's even see like the timeline of Java major release dates. Let's see how. Yeah, Java 1.1 was in 1996. 1.4 was in 2002, and then from 1.4 it jumped into Java 5, 6, 8, 9. So you can see like from 2009. Oh, the 2004 to 2006, that was one version. Then from 2006, from 6 to 7, it went from almost 6 years. And now it's almost yearly. So if we even were to chart that, it looks more like, you know, like if we were to chart the timeline from 1996 through 2021, you know, like it's much more compressed, the release timeline. I hope that answered your question, Nadia. Okay, Josh, regarding your question with Android, actually Android was not started at Google. Android was a separate project that Google bought at some point. But the reason why Android was written in Java is because of the right ones run everywhere. They wanted to have manufacturer freedom of choosing chipsets or any other electrical components, and they didn't have to worry about the apps working or not. If Samsung chose a different set of chips versus HTC or any others, they wanted a fast language that could work without any problems on a runtime. I think I lost. Okay, yeah, I was not. I didn't have you. Okay, that answered your question. Okay, all right. So then let's go back to the slides. Who's using Java now? And this is just a simple set of examples. I'll talk about a bunch of those here, but obviously Google. Their first MapReduce algorithm was written in Java. Still used very much throughout Google as a default programming language. Google still uses C++ and Python and Go for many of projects, but Java is still pretty much primarily one of the main languages there. The Spring Framework, which is one of the most popular frameworks for web development, is written in Java. Hadoop, which is a big data platform, which is a Google FS clone, and it has all sorts of anything big data, like the real big data stuff, is written in Java. Interfaces for working against those big data items might be written in Python, and that's why this is what I was saying about the data science certificate. That's why I wouldn't be surprised if they decided to include it, but not surprised that they didn't. Applications like TensorFlow or things that are, big frameworks for big data are all in Java, but they have interfaces towards being used in Python. So sometimes you're running Python, like for example, Spark, which is a framework for running MapReduce. It's written in Java. But if you want to write scripts, you can do so in Jython. Jython is a mixture of Java and Python, meaning you write the code in Python, and then it translates it into the intermediate bytecode that a Java virtual machine reads. So it's translated. It's kind of like Python, but in the surface, but it gets translated into Java because the runtime of Java is dramatically faster than the runtime in Python. So that's another one. And obviously, like Josh pointed out, Android apps are using Java now. And in Java 3, we go over simple Android apps as well, just to give you an arsenal of things to learn. Okay. So far, let's get some numbers. Disadvantages of Java. You know, I'm selling you on Java, but I also have to be real and honest. I don't want to tell you that everything is just magical and amazing. There's disadvantages, and I want to be real. The development process is slow, and mostly because it's very verbose. Things that in Java you can do, in Python you can do with one line. In Java you have to do it with 5 or 6 lines. So it adds a lot more typing. Deployments are complex. They're not as simple as in, you know, like a node deployment. You can just package it and send it. And the code, for that reason that it's quite verbose, can be long and ugly. And the number one expense on software development is human development. You know, like that's where the majority of any company that writes any software company, the great majority of their expenses is people writing code. So if the code can be long and ugly, either you need to have very strict guidelines of what the code should look like and make it as pretty as possible, or choose something else. And it all depends on your trade-offs. What you want with you want high performance, like you want to extract everything. That's why, you know, the big data frameworks, they want to extract every single CPU cycle from this. Or if you want, you know, maintainability, that's all based on the trade-offs. So those are the disadvantages. I explained this guy, but I want to just highlight one extra thing. You know, this is how, when we were talking about the translation, the output of the Java compiler is a class file. That's the one that it's distributed. In the case of a C++ program, the thing that it's, I forgot to add an extra block here, but that's the executable. I should redo this slide. That's the executable, and the executable is the one that is distributed. Here is the class file. So you're seeing how post linker, that's when the program is the one executing directly against the OS and against the processor, whereas in Java it's not even tied to the OS, it's not even tied to the processor, it's the Java runtime that actually takes care of that. Okay, let's see. I've been saying too much, and I want to make sure that I'm engaged with everyone. Let's give me some numbers, please. Some of the terminology that we're going to be using throughout this is the Java runtime, or the virtual machine. That's the thing that interprets the bytecode. The bytecode is the precompiled code that the virtual machine understands, and it translates to native instructions. We've talked about that. A package is a group of similar classes organized by folders and usually on a zip file. And a Java archive, which contains one or more packages for distribution. Speaking about that, so there is one of my new favorite Java applications that I want to also highlight as a user of Java. And it's Neo4j. And Neo4j is, actually, let's even see, for example, what is Redis written in. Oh, Redis is written in C. But if I look at Neo4j, Neo4j is a database that it's incredibly fast. Actually, in Gavalytics, we used it. It's written in Java. And it's a graph database that helps us to understand relationships between objects. And it's extremely fast. Like I was able to do operations that MySQL, Postgres, Snowflake, Amazon Aurora, all those were not able to do in the time that Neo4j would be able to do that. And it's all written in Java. I was, as a developer as a co-founder and CTO in Gavalytics, we were, let's see, 4.21. You can actually see jar. Let me see if I can make it a little bit bigger. This is essentially like the Java archives. Jar starts, it's Java archive. And if we open, for example, any of these libraries, I can actually see how, let me grab a small one. If I copy it here and basically rename that extension of jar to zip, use zip, you're gonna see that it is uncompressing all these. These are the packages, these folders. We're gonna talk about that. And these are the Java bytecode. So those are the contents of a jar file, that it's essentially the code that gets distributed and Java knows and understands how to unpack and execute. Okay, before we go into the rest of the code, let's get some, just, superficially at this point, we're going to go more in depth in the near future, but superficially, let's, up to this point, give me some numbers, please. Yes, it doesn't hold source code. It holds the precompiled class files. The Java files are the source code. The .class files are the intermediate translation. Now let's talk about how does Java look. We've talked a lot about the advantages, disadvantages, and all that stuff. But what I want is to now get our hands dirty and get ourselves into utilizing Java. So if you guys can, please download, go to IntelliJ.com or just go to Google and JetBrains IDEA, and you can download the community edition. An IDE is integrated development environment, and that has all the tools necessary for working together. So download the community version and install it. And also, you're going to download the JDK, and let's go for 1.8 right now. It's a long-term version, but you're going to go to the Java Oracle website and download the JDK for 1.8. We're using an old version. It's fine. That corresponds to your machine. So let's do that. And let's give you actually 5 minutes for the download and installation of those. Let's set up a timer.
Can we use VS Code, or should we download that?
You could use VS Code if you want to. I'm just gonna try to use IntelliJ because it's really easy to run the code, and I'm not gonna get into compiling by hand outside of this class. Outside of today, I'm not gonna compile by hand. It's just gonna try to make it as similar as possible to a Python runtime, but you can use whatever you want.
Sorry, what version of Java did you say from Oracle?
I've been using 1.8, but it could be any in reality, whatever you find.
I had previously downloaded Amazon Corretto. Will it give me the option of swapping the two?
Yeah, the community version. Then we're gonna open up IntelliJ, and let me just clear it all so that it looks exactly the way that yours is looking. I think you probably will be able to choose Corretto from the drop down in in IntelliJ, by the way. As long as you have a runtime that it's pointing somewhere. I'm actually surprised that Amazon was able to do their own runtime, because I think that there was a big lawsuit between Google and Oracle about Java at one point. So, okay, so when you launch, you get something like this. So we're going to create a new project. By the way, is everybody caught up, or do I need to wait for anybody? Okay, so then once we're in this window, we start with a new project. We're going to be basically using the same project for the entire quarter, just because it makes it simpler. So I'm going to select the top item, which is just a regular Java project. I can select whatever runtime I want from this dropdown. So if your Corretto shows up here, you can use that if you want to. And then hit next until then we create a project called Java 1. And I'm going to put it in my dev folder. We're going to create it. And now I have my IntelliJ project. When you first load it, you might get this little tab open. If you don't, it's open here. The left-hand side basically tells you the navigation of your project. Or if you switch into structure, you can actually see a class or something so you can navigate and jump between functions. The bottom part of things is command line utilities. And when you have enabled version control and building tools like Maven and things like that, they appear on the right-hand side. So if we are in this project, now we can click on the source directory. And we're going to right click and click on select new, and then Java class. And then we're going to put the name hello world. And I'm going to wait. I'm going to hit enter. And he creates a file called hello-world.java with a class hello world inside of it. You can see that the name hello world and the name hello world, it should match. Each file should match the class where the name of the class where it's stored. That's one way that Java knows how to find things. And I'm just going to wait for a second. Is anybody still downloading? Let me put a separator.
I downloaded the JDK 1.8 and then it was a zip file, and then I unzipped it. And then when I go into IntelliJ, it's like not recognizing the.
Oh, yeah.
tested.
Yeah. So usually what I would recommend is that you download the installer rather than the zip file, because the zip file is just essentially, you can put it in whatever folder you want, but the installer will actually put it in a default location where IntelliJ automatically will look for it. But you can, point when you're creating the project, you can actually say where the machine is. Cool. So now that we have hello world, I'm going to show you a couple tricks on IntelliJ. Any executable typically has what it's known as a main function. That means that tells the computer where you go into the program, where to start. So I'm going to type main and hit enter. This autocomplete thing shows up, and I'm going to hit enter. And now that I have that main, I'm also going to type this another shortcut, SOUT. And then I'm going to hit enter, and it will do the system out print. Here I'm going to put hello world. And the way to run it, basically, this is the first program that we're going to write, which means this is the entry point, and then we're just going to print hello world. The way to run it is we're going to right click on the file and then click on run hello world.main. And what it does is that in the background, it's compiling everything and executing it. So you can see how it ran and it printed hello world. So what is happening behind the scenes? Because I want you to understand You know, like I said, in the bottom, you see the output and the runtime stuff. On the left, you see the project and file related structure. So what happens if I go into Java 1? And you can see that IntelliJ, it's putting on the out directory, it's putting the hello world class, the compiled in an out directory. That's what IntelliJ does by default. But if I go into the source directory, you can see that there is a hello world.java. This hello world.java has what we just wrote. If I go up one level to the out and then go into the directory where it compiled it and just ran it. And if I look at the contents of the hello world, you're going to see that it's a binary file. This is a bytecode that the runtime will understand. Again, the .class file is the runtime understandable binary. Okay? Cool. Then how do we get from this .java to the other one? How do we do it by hand? We're never going to do this again after this class, but I want you to understand the process of how it happens. So there's this program called Java C, which stands for Java compiler, and we pass the file, the hello world.java. And now when we do an ls on the directory, we're going to see that it has the hello world.class and the hello world.java. Now to execute it, you run Java, which is the Java virtual machine, hello world, and we don't put the class file because it's just going to look for it in the predetermined location, which happens to be this directory. And now when I just run Java hello world, loads that class and executes it. I don't need to be recompiling it for every execution. So it's really fast the way that it does it. Any comments? Let's actually do some numbers until this point. Okay, so now that we know, we should understand like then every single word that it appears here. Public class, I told you guys that everything is object oriented. This public and class, we're gonna understand it when we talk about object oriented programming in class number 4. Public is static, we're gonna learn that. This is a data type that we're gonna learn also probably on the next class. But the only thing that I want to highlight is this string args. In any programming language, any program that you write, and that's actually like I want to, let's see. Oh, okay. So I imported these arrays to string. You don't have to remember this right now. This is just for me to show you what are those arguments. When you get something that it's in red, a good way to fix it in IntelliJ is you press in the situation of Mac, you press the Option key, and I think in PC is Alt, and it imports the library that you need to. Like it will show you like what are the potential fixes, and in this case, it just imports that library. So, what did this thing bring us? Well, any programming language, I mean, any programming command receives arguments, and basically is the options that you can pass to that command. So in reality, this Java C hello world, that's essentially an argument that we're passing to the command line. So if as I am compiling it, and now I do Java hello world, it's adding an empty parenthesis of arguments or extra data that I'm passing to the program. So I can do like pass some of your names. Let's see, George, Brandon, Nadia. And you can see how it passed each one of those separated by a space, made them a separate argument on that. That's just a way where we don't have to write every single value that our program is going to use permanently into the code. We can just pass it as arguments. Because we're going to be using IntelliJ and we're going to be doing it in a simpler way, we are rarely going to use the arguments. I just wanted you to understand that anything that is passed after the program will be sent to Java as arguments, to the program as arguments that you can read. So this just basically prints that array into a string. Okay. Let's ask the millennial, the centuries old question. Let's get some numbers on thus far on this. Okay. So now that we know that we can right click and run, there's another concept that I want to introduce. And I'm putting it on the first class because most programmers that I know rarely use this feature. And it's a shame. So I want to put it as a beginner thing. So there is this concept of a debugger. And the debugger is nothing else other than a tool that allows us to go step by step of what the code is doing in the computer and evaluating the values of each one of the variables internally. So for example, let's assume that I'm going to do int x equals 10. And then I'm going to create a breakpoint. A breakpoint is a piece in the code where the execution will stop, and it will and then we can evaluate what's happening. So after me creating a breakpoint, I'm going to right click and click debug hello world.main. And what it does is that it's going to execute all the way up to that breakpoint. And then we get this panel at the bottom. And in this panel, we have a few things. It's telling us where it stopped, which means in the main function, line 6, main function, line 6 of the class hello world. It's essentially telling us where the hell it is. Simple as that. Then it tells us what is in memory. And it's telling us, oh, it's the arguments that you received in the code and the variable x that has a value 10. So then we get all these controls on the top here, like step over, which allows us to go into the next line. You can go into step into, which in this case, it's going to try to evaluate the function if it has it available. Like in this case, because system.out.println is a built-in Java function, it couldn't go easily in. But if we really want to decompile the class and force it, we use this one as read. So let's go again and like rerun it. And now we're going to go force step into, and now it's going into this security manager, and we can go and start executing all these code to see what it's actually doing. So it's like we can go really deep into all those libraries, and you can notice that there's a lock icon. We're not going to worry about that right now, but it's a way to see like what is happening in case you need to. Then you also have step out. So actually, let's go force step in. If we did step out, what it's going to do is that it's going to take us back to where we were supposed to be. I pressed too much. Yeah, there you go. Now we're back into hello world. So it can make you go deeper down into a lower level view of what is happening, or you can exit that by using this step out. If we want to terminate our debugger, we can either press here, or if we want to continue the execution, even though that we have seen it, we can continue the execution by playing this resume program, and it's going to execute it. Why is this useful? Well, it's useful for it's just really useful for evaluating what is happening under the hood. So just FYI, this is a tool available for you guys, and I would like you guys to learn how to use it because it allows you to go step by step on the code. So when you are having a hard time, why you're not getting the right result, you can just add a breakpoint, get it to that point, and then execute from that point on where you're suspecting, line by line. Okay, let's then go into the super amazing question. Let's get some numbers so far. So for the first class, I think that there is, let me see what we have scheduled for. If there's a homework for the first class. I think the first class, it's a free pass. I just want to double check. Yeah, in the first class, we don't have any assignments. So first class is free pass. But I do want to give the 30 minutes for the one-on-one for whoever needs special help with setting up their environment. Because starting next week, we want to make sure that everybody is at the same spot. So for those of you that have it running and was able to run it or are not concerned about setting it up, class dismissed. It is lovely to meet you. I'm really excited to see where this class takes you. And I'll see you next week.